getting paid for both jobs and both jobs.
All right, we'll get started. First of all, thank you to Professor Nazrin for allowing me to give you guys a short introduction. My name is Brendan, and I'm part of the Curtin Motorsport team. This is a second year class, so hopefully some of you guys have heard of us. We are one of the university teams here at Curtin. We take part in the Formula Student competition. It's an international competition, but we take part in the Australian or Australasian competition, and it's held in Melbourne every year. And I'm just here to tell you guys a little bit about us. Hopefully, as engineers, some of you guys are interested, and there'll be opportunities for you guys to get involved, sign up. We've got our information night coming up, which I'll tell you guys a little bit more about. So yeah, if all of you guys could pay attention, that'd be great. Just in all these slides, if you guys at any point feel interested in joining up, there'll be that QR code that you guys can scan using your phone. It just takes you to our website, to the recruitment page of that. So scan it, sign up. It's just like a short form, and we'll direct you, send you guys some emails about all the stuff that's coming up for that. So yeah, what we do. So CMT, we used to be an IC class competition, so internal combustion engines, which is more for the mechanical guys. But recently we've ventured into the world of electric vehicles. So since 2022, we've been making EVs. We've made 3 cars since then, and we've been slowly progressing and improving. Just recently, last year, we came 3rd out of like 25 teams, so it was a big win for all of us, especially being only 3 years in the comp, while some teams have been there since like 2014, 2015, so yeah. As a team, we're divided into 4 technical sub-areas, so we've got aerodynamics, vehicle dynamics, tractive systems or powertrain, and then also the electronics area. So there's various different areas with various different expertise that you guys can all get involved in. Some more mechanical focused, some more electronics focused. So basically everyone has something that they can get interested in. And that's the car that we built last year. So that's, CMT2004. Single seater, similar to F1 for you guys that watch that. This is our mission statement. So basically we're trying to advance each one of our engineering knowledge and professionalism. So we try and apply the stuff that we learn here in the classrooms to basically a real world technical problem. And as well as that, we also focus on like the professionalism and soft skills that we develop in the workforce. So our management, leadership and communication skills. Along with the technical sub-areas, we also have about 6 business sub-areas, and we basically self-manage our own team as well. So there's a really good chance to get into that, and more like the project management side as well. And also, and what will be really interesting for you guys, we're becoming autonomous. So we're looking to move into the autonomous space. There's currently 3, what I would say, working autonomous vehicles in the competition, and that's rapidly increasing. So last year, Monash University did their first full run around a track, and just 2 years prior, they basically couldn't even get it moving. So it's rapidly increasing in like the improvement space. So we're also looking to join that as well. So we've had several thesis students starting off the designs, and now we're looking to build our own autonomous sub-team as well, which hopefully as some of you guys join up this year, you'll be able to get involved in as well. As I said, my name is Brendan. I've been on the team for 4 years now. I'm doing my final semester this year, so I might not get to see a whole lot of you guys, but this year I'm doing my thesis on the design and testing of the custom accumulator or battery segments. So we build our own battery pack as well. I'm in charge of basically the cell selection and also all the auxiliary stuff to do with that, so the cell connections, self-fusing, component selection, stuff like that, and also the cooling and packaging of it all. And so you'll see there, that middle picture, that's the battery segments. There's 5 of those in our accumulator or battery pack, and that forms the basically high voltage power that we use for our motor. Here's a couple of other pictures of our battery designs. This is just the packaging that we do at the start. So you can see here a couple of our boards for the guys who are into PCB design or electronics. We make a lot of our own PCB boards, so you can get involved with that. It's a lot of circuit design, prototyping, stuff like that. And then there's just packaging of other auxiliary components. So you'll see some contactors, some bulkheads or HVALs, depending on what you want to call them. And yeah, and we get to work on the car ourselves as well. So that's really cool. Hands-on experience as well, which you don't really get to learn in the classroom a whole lot. There's some more pictures. So I got told I was doing this about an hour ago, so I haven't managed to change it. But this is Isfan, who's, for you guys that go on and join, he's the current recruitment lead. So last year, he was a recruit, and his project was to design a low voltage battery for our car. So here he chose some cells. He had to spot weld them up himself. So yeah, if any of you guys like hobbyists who do like drone racing and all that, you might have seen these like custom built battery packs yourself. But yeah, so it's really fast, the development that you get on the team. So he did this after probably what would have been like 6 months on the team. So it's quite cool. And there's our full battery pack coming together. So that's 600 volts compared to what Isfan's was 12. Oops. So why become a member? Along with getting the opportunity to develop as your own engineer, you get the opportunity to apply the concepts that you've learned in class, and then you get to work on real life projects. It's also a great way to gain experience and also outreach as well. So you get the professional development through the team, and as well as that, you also get to work with a lot of professional companies currently working both in Australia and Perth, as well as also in the global scene as well. So some of the big names that we've worked with, SolidWorks, who we use for our modelling, ANSYS, who we use for our CAE or computer-aided engineering, so we do our CFD, our FEA analysis to them. Altium Designer for our board design, Loctite, adhesives, SKF, bearings, Tesla, that helped us out with our BMS or battery management system development, as well as our sales sponsorship as well. So these are some big names in the engineering space, and hopefully some of you guys might have seen those. So cool, what can you do now? So you can join us for the 2025 Information Night. That's coming up on Wednesday, the 12th of March from 6 p.m. Don't worry, you don't need to remember those dates. If any of you guys have scanned the QR code, you'll be able to get on that mailing list, and we'll send you more details to come. It's at the Elizabeth Jolly Lecture Theatre. Cool. So that's the end of my presentation. If any of you guys want to join, feel free to scan the QR code. And you can come see us. We're here on campus 206-151, which is just past the basement cafe or the engineering pavilion. I'll be here all day if you guys have got a couple of hours to kill after class. So yeah, come by, you can come talk to me, come talk to any of us, we're all happy to chat. So yeah, thank you, and thank you Professor Nazrin for allowing me to help. Cheers. Thank you.
Connecting. Stop working. Okay, this first video is an actually autonomous racing car. This video is from AMZ Racing in Zurich. It's an autonomous category. In the students' electric autonomous actually racing competition. So what we saw here, it's actually the characteristics or features of a mechatronic system. So we saw a mechanical system, which is the car, interacting with some environment, right? So there are some external influences there on the car, like the condition of the road, and also there are some obstacles on the road, including those cones with different colors. So, but if it was an autonomous vehicle on any other or any normal urban road, we had some other influences, like pedestrians, some other users, and some other things, right? Interacting with the vehicle. So actually the vehicle is perceiving its environment using some sensors, right? So one of the things you would notice here is actually the sense of display on here on the right hand side. This is showing the car seeing in terms of the its environment, right? These are the cones and the track, and this would be based on some sensors, maybe LiDAR or laser sensors, and some also visual sensing to detect the cones with different colors. And then those being mapped and trajectories being planned, as you can see here. I don't know if you have noticed, but it does actually one lap around the track slowly, just to actually map the location of the cones. And the second round was in full speed. Yeah. So we saw the mechanical system interacting, actually perceiving using the sensors and using some autonomous systems, making decisions and performing using actuators. This is actually the characteristics of any mechatronic system. Yeah. Let's see the second one.
Forgot my tools again. Such a show-off.
Okay, so this one was from a company called Boston Dynamics, and it's an example of an anthropomorphic robot, which is a robot in the shape of a human being with arms and with legs, and designed to perform some manipulation tasks. And you can see similar characteristics with the autonomous vehicle, but like with a different sort of mode. So we have, again, we have a mechanical system interacting within an environment, but this time the environment was a kind of construction environment. And it's able to perform action within that environment. So it's able to perceive that environment, so knows where objects are, and it's able to actually make decisions within that environment in order to accomplish some tasks and outcomes. Okay, very similar, right? The characteristics are very similar, but might be in different modes. And the last one, just watch a bit of this.
The Ingenuity Mars helicopter was designed to push the limits, and I'm going to show you how we've taken it to the extreme. Today, we're here in the Aerial Vehicles Lab at NASA's Jet Propulsion Laboratory, where we develop prototype helicopters. Ingenuity started off as a tech demo to push the aeronautical boundaries over the course of 5 flights. Then we transitioned into an operational demo phase where we partnered with the Perseverance rover to do science and scouting. But about a year ago, when the Perseverance rover started racing up the Jezero Crater Delta, we actually found that we had to work pretty hard to stay ahead of the rover. we decided it was time to shift gears again, once again pushing the boundaries of Martian flight. This campaign really began in earnest with Flight 49, where we simultaneously set new speed and altitude records. By Flight 62, we had nearly doubled our max speed and doubled our max altitude. We also tested different landing speeds, faster to save energy and slower to reduce landing loads. Both of these strategies may be used on future helicopters. We performed a type of flight testing called system identification. This is a crucial but risky procedure that helps us understand the vehicle's performance by how it responds. Our team also devised new ways to target the high-resolution camera, which allows us to provide advanced reconnaissance imaging for the rover. And we were able to take stunning shots like this one of Belva Crater from Flight 51. In addition, Ingenuity conducted several first-of-their-kind experiments on Martian wind and dust movement, which gave us new insight into the Martian atmosphere. What we've learned will help us design the next generation of Martian rotorcraft. We're testing more efficient blades. We're also working on a Mars science helicopter concept that could potentially transport heavier payloads and take us to more exciting locations on Mars. When people look back at Ingenuity, I really hope that they see how much this one small helicopter has done to elevate the limits of human achievement.
So again, here we see similar characteristics. A mechanical system operating within an environment, perceiving that environment, and performing actions on that environment. Obviously, when you are running a mission on Mars, you may consider other, environmental conditions, and your final project is a bit related to this one. It's very interesting. We will have a guest lecturer, I think week 4, and very interesting topic. Okay. People, myself, Jonathan Paxman, we have Tristan, who is the lead of the, all the labs, then Aman, Harry, Gabriel, Joaquin, and Alex. They are all very experienced, very knowledgeable, and I'm sure you will benefit from their knowledge and experience. But just when you are sending me any email related to the labs, just make sure that your lab tutors are CC'd. Okay, some definitions for mechatronics, some old ones like the design of microprocessor controller, mechanical systems. This is from Johns Hopkins University. Another one, the integrated study of the design of systems and products in which computation, mechanization, actuation, sensing, and control are designed together to achieve improved productivity and performance. And or this is another one from UNESCO, the synergistic integration of mechanical engineering with electronics and intelligent computer control in the design and manufacture of products and processes. But you usually see this diagram, which says mechatronics. It's actually including mechanical engineering, electronics engineering, and computer science. But in this course, I mean, in mechatronics course, you don't have all these things. You don't have all mechanical engineering, or you don't have all electronics and engineering and computer sciences. You just have like, it's a kind of about the interface between all these systems, okay? So especially for intelligent control of mechanical devices. Sometimes you see this diagram. So it's actually showing that like control systems, computers, mechanical systems, electronic systems, and it's got mechatronics somewhere in the actually intersection. Okay? And you can see the different types of applications, like in many different fields, like aerospace, medical, automotive, everything, yeah? You can see even in your daily life the application of the mechatronics. Any questions? Mechatronics, relative to other disciplines in engineering, is newer. It's actually during the 5 to maybe 10 years that it's really become popular. And I think that's because of the development of autonomous systems across of all aspects of industry, engineering, and really life in general. So a lot of autonomous systems out there at the moment, and the need for robotics engineers, autonomous system engineers, and mechatronic system engineers is really as high as ever been. Any questions? So what skills does a mechatronic engineer need? Any idea?
I guess skills in all those things that you pointed out.
Yeah, yes. Like computer programming, this is essential, right? Embedded systems programming, so it's programming a microcontroller which is interacting with sensors and actuators, and sometimes with some user interface devices to perform some actions in real time, real world applications. Also, the ability to apply mathematics to real problems. Mathematical modeling actually help a lot to understand the behavior of the system and predict it. Analyze and design digital and analog systems, mechanical systems. You need to think across disciplinary boundaries, and very important, problem solving. When you graduate as a mechatronic engineer, you will have the language of almost like mechanical engineers, electronics engineers, and computer programming. That's really good, and will put you in a really important place when it comes to working on those large and complex projects. How about this unit? This unit is a actually lab-based unit, and as you know, there is a 3-hour lab every week in which you use a microcontroller to communicate with sensors, actuators, and input devices. You need to work effectively in teams and build a mechatronic system based on the microcontroller to achieve the project task. The labs are very fundamental, and the lectures are really supporting what you do in the lab. Lecture is actually kind of a briefing that gives you the fundamentals to be able to go into the lab and practically implement what you have learned, not just in this unit, but the other units that are related to, like electronics major. Unit learning outcomes apply a top-down approach to design a mechatronic solution for an ongoing problem. You need to program a microcontroller using a high-level language to solve an engineering problem, and then design and build analog and digital circuits to interface between a microcontroller and sensors, actuators, and I/O devices. You will work in team, group of 2, sometimes 3, and documentation is very important in this unit. So you need to have a lab book to document all your work, and it can be a physical lab book or a digital one. No exam. We have 8 assessed weekly labs from 1 to 8, which is just 40% of the total mark. And they will be marked during lab time on specific technical and documentation milestones. You will see all the details and tasks in the lab descriptions. You have one assignment. It's called assignment 1, which is a virtual microcontroller programming task accomplished through Tinkercad. I don't know if you have used that earlier. Mm-hmm. Okay. More information will be released a bit later. And the final robot project, 40% of the total mark, and comprising technical outcomes, competition performance, and a report. So it's very important to utilize your time for your lab, because it's very limited, and we cannot offer any extra labs. We have 8 labs, almost 140 students. So do a lot of preparation before labs, please. That's very important, to come to the labs prepared, very well prepared. I think you all are familiar with Blackboard, right? Have you checked it, our unit details? Mm-hmm. No? Isn't it? You couldn't find the materials, or? No. Really? Okay, I'll check it. Yeah, I'll check. Because I uploaded everything last week. I'll check it. Maybe you don't have access. Yeah, I'll check. Yeah, thank you. I'll just make a note. So you can find everything there: unit outline, technical data sheets, some tutorial material, and links to lab task description, Could you see anything for like lab material, some videos? Okay, those are okay. Those are very useful, very helpful if you can go through them before the labs. So that gives you idea what you are going to do in the lab, and you can get very well prepared. GitHub. We have some unit materials in GitHub. You can join. I don't know if you have checked this GitHub material yet. Mm-hmm. Okay. So it contains the project framework we will use for all labs and the final project. You will also find code examples, some tutorial material, and lab assignments. You don't need a GitHub account unless you want to create your own for it. And the discussion forum, this is very useful. And it's intended as a place to discuss lab and project work and to ask and answer questions. Though lab demonstrators and myself will answer questions, but I strongly encourage students to answer each other's questions or to post solutions to problems that you encounter. Please post general questions to the forum instead of emailing staff. Also check to ensure that someone hasn't already asked the same question. Anyone has tried to join this? Not yet? Okay. Just try and let me know if there is any problem. So you need to have a lab book. As I said, it can be digital or physical. Documentation is very, very important because whatever you are doing in weekly labs, for the final project, you will need them, and you are going to actually put all together. So it's good to have all your work in a same place, and you can easily access them. So, and as I said, lab time is limited, so reading and preparation is very important and essential in this unit. Comments in the first week. Please ensure you are registered for labs and consult your timetable, read the lab briefing, view the lab briefing videos. These videos are very important, very, very useful actually. Use of GenAI tools, including ChatGPT. This is actually a description that was given by ChatGPT. But the things to be aware of when you use that, you cannot trust the output. ChatGPT especially is capable of producing plausible, confident, and wrong answers. Code produced using ChatGPT or other tools may or may not compile correctly, and it may or may not produce a correct result. So debugging skills are of critical importance. So you need to have the fundamental, and you should be able to debug it. Be aware of using GenAI tools as a crutch when you don't know the fundamentals. And sometimes ChatGPT can explain what it is doing, but again, that might not be always correct. Yeah. So policy on use of GenAI in this unit, unless specific instructions exclude their use, GenAI tools are permitted. Indeed, I would encourage you to spend at least some time experimenting with the capabilities and potential uses of the tools. Any code or other text which is utilized as part of an assessment must be acknowledged with the following details, like the name and URL of the tool used, any text prompts, and outline of any modification you made. You are responsible for ensuring the correctness of the code that you use. You are responsible for ensuring you understand what your code is doing whenever it is used in an assessment task. And the lab demonstrators may check that you understand what your program is doing before awarding marks. Any questions? Okay. Let's move to a bit more technical topic. And let's start with the heart of this unit, Arduino Mega Board, or Mega 2560. Who has programmed an Arduino before? That's good. But I think some of you have seen probably Uno board, not Mega one, Mega, it's like a smaller board. Yeah. But that's okay. If you haven't seen or used any Arduino before, that's completely okay. No problem. In this unit, we are not assuming that you have seen or used any Arduino before. Okay? So this is the board that's got a microcontroller and the power connector. It's got a crystal that produces a 16 megahertz clock. USB port. It can be programmed, and also for some data interface with computer. We have digital I/O pins. They actually help us to interface with sensors and actuators. So it can read digital inputs and write digital outputs. We have analog input output pins. So we can analog voltages using these pins. A reset button. Yep. So, as I said, this is the heart of this unit. You will work on this throughout the semester. So, what is a microcontroller or micro? It's a single chip computer that can handle input, output, and computation. So it can gather information from sensors, process the input into a set of actions, send output signals to do something useful. But input also can be received from user interface devices, like in this unit, we are using push buttons or joysticks, or wireless communication in some cases to receive data. can be used on a wide range of different tasks and applications. There are many manufacturers and models to choose from, and they all behave in similar, actually kind of way, but the interactions with them might be a bit different. And the one we are using in this unit is at MXEN2003. So it has uses 8-bit processor with a speed up to 16 megahertz. That is because of the crystal which has. It has some RAMs and flash memory, 8 kilobyte, 4 and 256. It's not a lot. That means the programs cannot be huge. Analog to digital converter, some serial interfaces, up to 4 of them, PWM, pulse width modulation. We'll get to that later. That's a very important topic. Many I/O pins, 86, and it can also do some internal counting and timing. So on a microcontroller, we have a limited memory, speed, and processor capabilities. So we need to think slightly actually different compared to the time we are doing actually programming on a desktop computer because of these limitations. If you want to do a high-level mathematical operation on a desktop, there won't be any issue that can be done so quickly. But on a microcontroller, that's another issue. So microcontroller cannot do those high-level operation processes very fast. Adding, subtracting, and sometimes multiplying can be done quickly, or anything dealing with integers can be done fast, but anything dealing with floating point numbers can be a little slow. So you need to consider these things during your programming. There are different languages we use. We can use actually, but in this unit we use C. So, as I said, you need to consider these things. Some operations are fast, like logical operations, bitwise addition or subtraction, and memory access. Integer multiplication with these macros is pretty fast because it has a hardware multiplier, but not all the macros have that one. And some operations are slow, as I said, and some very slow. So anything that is higher order math, very, very slow. Any questions? Sorry? Okay. This is a diagram of MXEN2003. It has 11 8-pin general purpose I/O ports. 86 pins are available on the micro, and of these, 70 are accessible from the Arduino Mega. Just be aware that the board pin numbering is different to the microcontroller numbering. And 2 ports, F and K, can also act as an ADC for reading analog voltages. You may wish to consider purchasing your own Arduino hardware. It's not compulsory, but I do suggest you to have your own Arduino board. So you can use it anytime. In the labs, we use the Arduino Mega or Mega 2560, but you can find the compatible boards in lower prices.
Just go straight to AliExpress and get them for $5.
Yep. Arduino has its own pin numbering system, which is different from the microcontroller port labels. To use the port labels, like port A, port B, etc., you will need to look up the pin associations, either on the Arduino schematic or other references. You can easily search it. Yep. Okay, bit of review. Because we will be using a lot of binary in this unit, and I'm sure you all know about these things, just a revision. So you know that computers store numbers in a series of switches, which are either on or off. And the natural way to represent an integer is as a binary expression. This is one example for like number 45 in base 10 or 2D in base 16 or in hexadecimal format. So we can use hexa representation just as shorthand. In C, a hexadecimal representation is denoted by the prefix 0x, or it can be for base 8, it can be just 0, and 0b can be for binary representation. Any question for this one? You just need to review this thing. I know you all know about this thing. Might be a bit boring, but yeah, it's good to review once. You are mostly going to, these are different. You can check them later. You are mostly going to be dealing with unsigned integers in Arduino. So just like some binary operations, addition, subtraction. Addition is so straightforward, and subtraction you can use 2's complement for the second number. This is one example. It should be clear, right? And two's complement is useful to understand the overflow behavior when working with signed integers. Mostly we will work with unsigned integers in this unit and with Arduino. Bitwise binary operations, the logical operations. You've probably dealt with logical operations in your first year programming unit, I guess. So we have not, which is actually flipping all of the individual bits, right? And we have AND. So you can see the result is 1 if the corresponding bits in the two numbers are both ones. Otherwise, it's 0. Or the result is 1 if either A or B has a 1 in the corresponding bit. Otherwise, 0. We use them a lot in our programming. XOR, exclusive OR, the result is 1 when A or B is 1, but not both. And then NAND and NOR, but the first these four actually, NOT and OR and XOR, are the 4 binary operations we use a lot. Any questions so far? Bitwise binary operations, shift left and shift right. This can be useful in your first lab. So yeah, this is equivalent to multiplication or division by 2, but you need to be careful for overflow. Registers and digital input-output. Registers are memory locations used for particular hardware purposes. Atmel microcontrollers have registers associated with each I/O port for input, output, and data direction, and most of them are 8-bit registers. The first one that we have to deal with is the data direction register, DDR, which tells the microcontroller whether each pin is used for input or for output. You will use this one for your first lab. So DDR just decide whether a particular pin or bit in a particular port is being used for reading or for writing. Ones represent outputs and zeros represent input. For example, this one, DDR-A, is actually setting the data direction for each pin on port A. So this example here sets the upper nibble on port A as output because of ones, and the lower as input because of these zeros. Or the next example is actually setting the whole of port K as output because of ones. They can be actually set individually, or we can use this shift operations to set them. So this actually sets pin 2 port K as output. Or we can use this to make as input. This is another way to set them. Ports writing. Output ports can be accessed directly using the port X register, where X is the port letter. It can be A, B, or anything. So we can write the entire port once, like this example. So in this example, we are writing like different ports at the same time. Or it can be shown in hexadecimal representation. But before using these, actually like writing this, you should set the DDRX high, because that says that if it is input or output, right? So first you need to set DDRX high before writing, and then you can use port A and to set the writing, the ports as writing. So port bits can be set individually using an OR operator or cleared using an AND operator. Like the same as these examples used for DDRX, we can use this similar actually way to set them. So the first one sets the bit 2 only, and the second one clears the bit 2 only. We can use the bitwise shift operators to do this more compactly, the same. So the first one is actually setting the bit 2 only here, or we can use bitwise shift operators, exactly the same, or even more compact version is this way, that way. So you can use any of them. And you can use AND operator to clear the bit 2 only, like here in this example, or you can use bitwise shift operators and even more compact this way. Okay. Arduino boards can be programmed using the custom Arduino language or other suitable languages for embedded controller like C. We will focus on the C language and a development environment called Visual Studio, which is free, very powerful, and flexible, and suitable for all types of Atmel microcontrollers. You can find sample code and project files through the GitHub repository. You may be familiar with the Arduino development, which can be downloaded from Arduino website. But we will not be using the Arduino environment in this unit. It's easy to use and can be useful for rapid prototyping and testing, but we are using C in this because that can be used for all types of Atmel microcontrollers. And your first program, this code actually gives you idea to start lab 1. Then you can work on this code, develop it, and complete lab 1 tasks. It's very simple program. We have the main loop. So, because, see, this is DDR-A and then port A. The same thing we just discussed, right? So here, it's actually putting port A into output mode, right, for writing. So, and here we have the main loop. All the initialization and setup code should come before the main loop. So we have it here. This is the main loop. We have initialization codes before that. And we have global variables which are defined outside the main function. Okay? Very simple code, but you can work on it to complete lab 1 tasks.
There's 1,000 ways you can achieve the same thing. How strict are you going to be on exact techniques?
I'm not straight on. So you need to complete the task. That's in a proper way, you know. But we have developed some structures for you to make things a bit easier. Any questions? These are actually, like, the project task was completely different last few years, but this year we are trying to change the scenario. We'll discuss this a bit later. It should be very interesting. Any questions? This is like for last year's.
Something that's noticeable is that it's much faster driving autonomously. Seems that manually drive.
We had some symbols and like victims. You had to find them. Okay, thank you. Any questions?
I'll